Hi dear students, so let us discuss about the rolling motion. So in the beginning of this chapter we have already discussed that the rolling motion is the combination of translational and as well the rotational motion. So here in this picture on this diagram you can see three particles, one P0, P1 and P2, and the C is the center of the mass. So the axis of rotation is through the center of the mass, and which is perpendicular to the plane of the screen. Okay, consider like that. So the axis of rotation which is perpendicular to the plane and which is passing through the center of the mass. And here the angular velocity value it is given as omega, and the center of the mass it is velocity, with velocity vcm, the center of mass it is moving vcm. So here the translational velocity will be vcm. Okay, so the translational velocity of this rolling motion it is vcm, that is the velocity of the center of the mass. Now, so as we have said, the rolling motion is the combination of the rotation and translational motions. Vector vcm is the velocity of the center of the mass, and the value will be the direction of the vcm, velocity of the center of mass, will be parallel to the level of the surface. And the rotation motion is about the symmetry axis which is passing through the center of the mass C, that we have already discussed, which is perpendicular to the plane. Now let us consider the points P0, P1 and P2. Consider that are three particles and P0, P1 and P2. So if you are considering the velocity of a particular particle, suppose considering the P2, the velocity, it is having two components. One it is the vcm and another one it is the vr. The velocity v2 is actually the linear velocity which causes the rotational motion. Okay, the P2. For the particle P2, v2 is the linear velocity which causes the rotational motion. And VR, you can see the velocity direction VR. Actually, if you are considering a circle, a concentric circle which is passing through P2 and the center at the same center, the center of mass, if the center of that circle it is, if you are considering, the VR will become, or we can consider the VR as the tangent of that circle at the point P2, and the radius is R2, here R2. So radius and tangent will be always perpendicular to each other, hence here the term VR, the component of the velocity VR, will be perpendicular to the radius. So here the linear velocity VR is the reason behind the rotation. And the resultant velocity of this vcm and VR is the v2. So VR is the linear velocity which causes the rotation, vcm is the velocity of the center of mass, and that is the translational velocity of this particular rotating body, and v2 is the resultant velocity of the particle at P2 due to this VR and vcm. And VR will be always perpendicular to the radius which is in between the radius or the line which is joining the center of mass and the particle. Okay. Hence the rotational velocity or the angular velocity and this VR can be related as VR is equal to, here the radius value it is R2, so R2 omega, or if you are taking this R2 as in common as R, the radius of the circular path if you are considering, then R into omega. So VR will be is equal to R omega. Now if you are considering the point P0, the linear velocity VR will be in the opposite direction of the translation velocity VCM. At P0, the VR will be, that is the VR will be adding in this direction and VCM in this direction. So VCM and VR are opposite to each other. And at P0, the velocity value will be, the combined velocity value will be 0. Hence, VR will be is equal to VCM. Okay. So VR will be is equal to VCM. Hence, VCM can be written as R omega. Here the radius is the total radius of the circle. So capital R will be the radius value. So capital R into omega will be the VCM value if you are considering the point P0. Okay. So now if you are considering the point at P1, it's the point over here. The direction of VCM and the VR both are in the same direction. So total velocity V1 will be equal to VC or VR plus VCM, where both values are R omega with the same and equal and in the same direction they are. So 2 R omega will be there. Hence V1 will be equal to 2 R omega or 2 VCM. So V1, here the resultant velocity V1 at the point P1 will be equal to 2 R omega or 2 VCM. Okay. Now let us discuss the kinetic energy of a rolling motion. Actually, in the case of this kinetic energy of the rolling motion, you have to consider the kinetic energies of the rotational motion and as well the translational motion. In the case of the translational motion, you know that half mv square is the equation for the kinetic energy in the translation or the linear motion. Here the linear velocity is actually VCM, hence that value will become half m VCM square. And here K dash it is representing, K dash is representing the kinetic energy of the rotational motion, and already we have discussed in the comparison of the linear velocity and linear energy and as well the kinetic rotational energy, we have seen that the correspondent or the analog of mass in the case of the rotational motion it is inertia and velocity it is omega. So combining the two values you can design the kinetic energy of the rotational motion as half I omega square. So K dash will become half I omega square. Okay. And here suppose that radius of gyration I is equal to mr square, that we have already studied. If the r value, that is the radius of gyration, if it is a random number k, then I will be is equal to m k square. Okay, I will be is equal to m k square. So substituting the value of I here in this equation, here you have to substitute the value of I as m k square. Then the equation will become half of m k square into actually r omega is equal to VCM. So omega will be is equal to VCM by r. So this omega square will become is VCM square by r square. So instead of I, you will be getting mk square, and omega square will become v square by r square and half mvcm square. So the kinetic energy value will become k is equal to half mvcm square, you are taking as common, into 1 plus k square divided by r square, where k is the radius of gyration and r is the radius of the particle or the circular body. VCM is the linear velocity, or we can say the velocity of the center of mass, and m is the mass of the body. So the total kinetic energy of a rolling motion will become half m VCM square into 1 plus k square by r square. So now you just go through the exercise question answers and practice the questions. I will just send you the links for the hints of that questions. Now refer that link and try to solve yourself. And if you are having any doubts, you can ask me and we will clarify that doubts in this chapter. Okay, thank you.